Let's do a problem related to Cramer's rule. 4.3, section 4.3, number 31 says, solve the system of linear equations using Cramer's rule. Not an efficient way of doing it, but we want to illustrate it. 3x1 plus 2x2 minus x3 equals 1, x1 minus 4x2 plus x3 equals negative 2, 5x1 plus 2x2 equals 1. Only 1, 0. If we were to do it with row reduction, we'd, I guess, have to do a fair amount of work. But the instructions are use Cramer's rule. So let's recall what we've got by Cramer's rule. By Cramer's rule, we have that solutions of such systems of equations, say x sub I, are given by the determinant of a matrix B sub I divided by the determinant of matrix A. This will be good for I equals, in this case, 1, 2, and 3, where, all right, and here comes the bad news. We need a bunch of determinants. Matrix B sub I is obtained from matrix A by replacing the ith column of A by vector B. Here, where, let's see, we've got matrix A as a coefficient matrix. So usual notation, we're taking this and thinking of it as AX equals B. So the B vector is the stuff on the right-hand side. The A matrix would be the matrix of coefficients. So 3, 2, negative 1 for the first row. Negative 1, 1, negative 4, 1, second row, third row, 5, 2, 0, and vector B would be the right-hand sides as usual. And I tell you what, let me color code that because I got my reasons. Vector B would be the column vector 1, negative 2, 1. Okay, so of course the bad news is we've got to take determinants of A, and that's 3 by 3, it's going to be worse, and B1 and B2 and B3. So that's 4 determinants of 3 by 3 matrices. Okay, well, let me prefab some of it here. So, we need the determinant of matrix A. Let me show that one in detail. Okay, so 3, 2, negative 1, and so forth. Let's do some row reduction first and simplify it, keeping track of how the row operations affect the value of the determinant. Okay, see this 1. Let's swap row 1 and row 2 to get a 1 up here. Then we'll use that 1 as a pivot, and we'll eliminate the things below the 1 as usual. Swapping row 1 and row 2, that changes the value of the determinant by a negative sign. So we'll have to introduce a negative sign here. Now we'll take a determinant of this, but first let's row reduce. So we'll take row 2 and subtract 3 times row 1 to get a 0 here. We'll take row 3 and subtract 5 times row 1 to get a 0 here, and some other arithmetic things happen. Now we've got a matrix, at least got a couple of zeros in it in convenient places. We've got 2 zeros in the first column. We could go further with the row reduction stuff. That doesn't look terribly promising with these particular numbers. Let's take the determinant at this stage. Maybe you observe as well. Hey, these row operations, I love these guys. They introduce zeros and they don't change the determinant. So these are useful things in terms of computing determinants. So let's take this negative sign out front. Be careful with all the negatives. We'll have this entry times the determinant of the associated minor matrix, 14, negative 4, 22, negative 5, as given there for rows, minus 0 times something or other, plus 0 times something or other. There you go. So take advantage of the zeros. Taking a determinant of this 2 by 2 matrix, diagonal, minus, off diagonal. Be careful with parentheses and negative signs. And when all the dust settles, we'll get negative 18 for the determinant of matrix A. All right, so matrix B1, B sub I, should be obtained from matrix A by replacing the ith column of A by column vector B. So matrix B sub 1 should be 1, negative 2, 1 as the first column, and the second and third columns the same as matrix A. So looks like we got a little typo here. Should have a negative. It's a negative 4. Wasn't that entry? That should be a negative 4 here. Where's my black pen? Should be a negative 4 here and a negative 4 here. Okay, so let's see. We got it right now. Yeah. So first column, column vector B. Second and third columns the same as matrix A. Let's take a determinant of that. Okay, I've got written solutions for you, and they're posted online. I'd use this 1 to eliminate the negative 2 and the 1 here. Similar row operations as we have upstairs of this type, preferably. Anyhow, we'll go through the computations. You'll find out the determinant is 0. Give me a little break on my limited space here. But detailed solutions are written out for each of these determinants in the supplement. B sub 2, we take matrix A and replace the second column with column vector B, producing this. If I were me, I'd probably swap those first 2 rows, introducing a negative like we did over here, use the 1 to eliminate the 3 and the 5 like we did up here. Of course, it's not the same computation because the blue numbers are different from what we had from the center column upstairs. But I'd do similar manipulations, probably to compute the determinant. We'd find out we get negative 9 out of that one. B sub 3, take matrix A, replace the third column with vector B, compute the determinant. It's worth your trouble to do some swapping and some row reductions. For these second two, you'd probably do similar things as what's given here. And you'd find that the determinant of B sub 3 is also 0. So Cramer's rule says we get x1 is determinant of b1 over determinant of a. So it'd give us a 0 over negative 18, or 0. X sub 2 is determinant of b sub 2 over the determinant of a. That'd give us a negative 9 over negative 18, so half. And x sub 3, determinant of b sub 3 over determinant of a is also 0. So there's most of a solution of using Cramer's rule to solve a system of equations. Yeah, you've got a better way of doing it. Gauss-Jordan elimination is computationally a whole bunch quicker. The delay, of course, is in taking these determinants. It's worth your while to do some row reduction before you compute determinants. You got to do 4 of them. I guess the only good news I got for you is, well, the row reduction you did for matrix A will be super similar to the type of row reduction you do for B sub 2 and B sub 3 because the first columns are the same.